Hello everyone, my name is Devon Hockley. I am a student at the University of Calgary. I will be presenting our paper, Benchmarking Runtime Scripting Performance in WASMer. This work was done in collaboration with Kerry Williamson, a professor at the University of Calgary. In our paper, we seek to demonstrate WASMer in a runtime scripting environment. This would allow a program to be extended using a variety of languages in a secure way. We explored a series of techniques to implement these calls into user code hosted in WASMer, both in an artificial micro-benchmark to evaluate things in a fine-grained manner, and a more realistic macro-benchmark to see how these results carry over to real applications. First, a brief overview of WebAssembly. It was created by the W3C and members of the Bytecode Alliance as a sandboxed multi-language environment for web browsers. It coexists alongside JavaScript and can interoperate with it to perform operations on the DOM and other browser functions. It is designed to allow for the deployment of low-level, high-performance code in a safe, sandboxed environment. WebAssembly, or WASM, is defined as a low-level bytecode that is similar to a static machine. It doesn't currently provide any garbage collection, classes, interfaces, or any higher-level types beyond basic primitives. Specifically, it only supports 32 and 64-bit integers and floats natively. While a WebAssembly text format does exist, as pictured here in the top right, it is primarily designed as a compilation target for other languages. Languages that can target WASM include Rust through its LLVM backend, C and C++ through Mscripton, C# through Blazor, and WASM native languages such as AssemblyScript, which is a derivative of TypeScript. This bytecode is then processed by the WASM runtime, either being just-in-time compiled to native assembly or sometimes interpreted. In addition to those embedded in browsers like Chromium and Firefox, there exists WASM virtual machine implementations independent of browsers. There are a couple of note to this paper, the first of which is WASM Time. This is a sort of reference implementation of the WASM standard created by the Bytecode Alliance. It includes a custom compiler backend called Cranelift, which can also be used as an alternative to the LLVM in the Rust C compiler. It is written in Rust, as is the parent WASM Time project. Cranelift currently compiles code much faster than the LLVM, however, as a trade-off, it has fewer optimizations it can perform. The other implementation we examined was WASMer, and is the one we used to implement the benchmarks. It was created by WASMer Inc. and supports multiple JIT backends, including the same Cranelift compiler from WASM Time, as well as the full LLVM and their own in-house Singlepass compiler. Based on these implementations, there are a variety of applications that use WASM outside the browser. Two examples relevant to this paper are the Lunatic runtime and the open-source video game Valorant. Lunatic aims to be a language-independent alternative to the Beam virtual machine, running many small virtual processes in parallel across multiple computers, optimized for high concurrency and high reliability. These processes are implemented as WASM modules, executed using either the WASM Time or WASMer virtual machines at the developer's discretion. It favors many small processes, such as creating a new process for each incoming request so that they may be handled concurrently, and also ensures that any crashes are automatically contained and won't crash the whole runtime. The other example, Valorant, is a open-source 3D video game written in Rust. It uses WASM to allow for user-written code to be loaded at runtime in the form of plugins to modify gameplay or expand the game. These plugins are WASM modules that use an event-driven architecture. This means that the plugin would contain small methods like click handlers, on-hit handlers, and other such event handlers, which are invoked by the game when those events happen. We did find a previous paper benchmarking WebAssembly from the University of Massachusetts. They found up to a 2.5 times performance penalty when comparing the spec benchmark running in WASM to the native performance. By using the spec benchmark, this benchmark focuses on a well-known, long-running benchmark suite. This test was also run using WASM implementations in browsers instead of standalone ones like WASMer or WASM Time. We were unable to find any papers benchmarking these standalone implementations. In our paper, we explore the performance of WASMer in application scripting environments, specifically to measure any additional performance penalty when making many small function calls, such as those in systems like Lunatic and Valorant, which favor many short scripts. This is a different workload from full applications like those tested in the paper from the University of Massachusetts, as those full applications are very large executions, instead of making thousands of short calls into WASM, returning to the host application's native code in between, like Lunatic and Valorant. We implemented our own program on top of WASMer so that we can have the full level of control required to compare different implementations, which could then be used to construct programs like Lunatic and Valorant. Now I will go through an overview of our experimental methodology and the program we created to implement it. We used the Rust programming language to create a small benchmark program on top of WASMer. This benchmark tests various methods of calling into WebAssembly from the host program, different ABIs, different configurations. Rust's correctness features, performance, and low-level memory control made it well suited to making this program because it gave us the low-level control and also allowed us to integrate directly with WASMer instead of having to go through a non-native C ABI. The backend modules were also written in Rust since it has a very mature WebAssembly backend through the LLVM, and the low-level memory control helps us create our different ABIs for our benchmarks. This table shows the different factors that were tested in our experiments. The main factor we tested was 3 different ABIs, which we labeled pair, Bytemuck, and BinCode. For each of these ABIs, we tested caching the reference to the compiled code, which is essentially caching the function pointer for the function we want to call. For pair, we tried an additional form of caching called self-referential struct. This structures the data in a more object-oriented way, where we have a plugin struct that contains references to both the compiled module as a whole and the function pointers themselves. This is a more realistic configuration that is meant to represent how real software might want to store these pieces of data. For the pair ABI, we tested what effect loading the arguments on every function call had in comparison to storing them once and passing by reference. These are labeled as hotload and preload respectively in the table. The other 2 ABIs require memory allocation within the WASM sandbox, so we tested both dynamic and static allocation for these when possible. BinCode does not seem to be capable of using the static allocation method, so only dynamic was tested for that. For each run, we called the method in WASM a couple thousand times and saved the total time for that run. We then performed this total run multiple times and took the average to ensure the accuracy. This process was done for each of the 12 implementations in the table in sequence in one run of the benchmark program. This test suite was run for both the release and debug mode, as well as across 3 different JIT backends for WASMer, so a total of 6 runs. The debug and release modes are flags in the Rust-C compiler, and the 3 different JIT backends are the Singlepass compiler, created by WASMer that favors really fast compilation times, but doesn't really optimize the code. The LLVM backend from the LLVM project, full compiler backend with support for many optimizations, but compiles fairly slowly as a result. And the Cranelift backend, which falls in between the two with faster compile times than LLVM, but more optimizations than Singlepass. I will now do a brief overview of our 3 different ABIs. The first ABI we tested was pair, which passes the data as normal arguments using a standard C ABI. Very simple to implement. We just need to annotate the code to tell the Rust compiler to not mangle the symbols. However, this is limited to basic integer and float types because of WebAssembly's restrictions on types. The next ABI we tested was BinCode. For this method, we first make a call into the module to allocate a small buffer, returning a pointer to it and the length of that buffer. We then use a library called BinCode to encode the struct into bytes and copy it into that buffer. Finally, we call the main method in WASM that we wish to invoke, passing the pointer and length as arguments. The module then uses those to deserialize the buffer back into a struct that it can understand. Our final ABI, Bytemuck, uses a process very similar to the BinCode ABI. However, instead of serializing and deserializing the data, we cast the data as a C struct and copy it directly. This has the advantage of meaning the size of the data is known at compile time, so we can actually use static allocation instead of dynamic allocation. Since Bytemuck just checks memory alignment, it should be much simpler than BinCode. However, it can only represent types that can be represented directly as a C struct and not more complicated types like BinCode is capable of. Finally, I will give a brief overview of the architecture of the macro benchmark that we created based on these micro benchmarks. We decided to use a web caching policy simulator using a similar architecture to the micro benchmark program. In this simulator, each web caching policy is implemented as its own WebAssembly module. We load a test file from disk and feed these events one by one into each policy, with each event being one function call into WebAssembly. Certain factors were skipped, such as dynamic memory in the case of Bytemuck due to performing strictly worse. We tested 4 policies in order to try and stress the system in different ways. The first policy we tested was FIFO, or first in, first out, just to test using a queue. Both least frequently and least recently used were implemented using a priority queue. And finally, GD size was implemented using a standard binary heap. For all of these algorithms, the cache state itself was implemented using a hash set, and the other data structures were used simply to decide which was next to evict from the cache. To validate the correctness of our program, we compared the results to an existing C implementation of the same algorithms. Each algorithm was tested using a trace file that contains 1 million cache requests. This translates to 1 million calls into the WebAssembly machine, one for each cache request. For each caching policy, we ran through the test file 10 times, averaging the results. Now I will go through the experimental results of our benchmarks. First, we will examine the micro-benchmark results. This first graph shows the results of the Singlepass run of the benchmarks. As can be seen in the graph, the cached implementation performed better than the uncached one for all implementations. We can see with the Singlepass compiler that the Bytemuck implementation performed the slowest, followed by bin code, followed by the static allocated Bytemuck. We can see that for the pair ABI, the hot load versus preload factor made essentially no difference. This is most likely because the hot load version was optimized into the preload version by the compiler in release mode. While the pair ABI may have performed the best in comparison to the other WebAssembly ABIs, it's important to remember that it has rather limited usage because it doesn't support anything more complex than integers and floats. When we switch out the backend for Cranelift, the performance improves somewhat. Most notably, the dynamically allocated Bytemuck result closes in on the bin code results a fair bit. We also see the hot load version falls slightly behind the preload version of all the pair ABIs. However, pair does continue to be the fastest ABI, second only to the static Bytemuck ABI. In comparison to the Singlepass backend, the Cranelift backend compiled code only slightly slower, most likely because the code itself is very simple. Finally, we have the results for the LLVM backend. Unfortunately, LLVM did not improve the code substantially. This is again most likely because the source code being compiled is extremely simple. This is intentional because we want to focus on the performance of the actual function call into WebAssembly, not the performance of the code within WebAssembly for these microbenchmarks. Compilation speed was drastically reduced, however, which can be seen on this graph here. Once we include the compilation times, LLVM almost quadruples its times in comparison to the Cranelift and Singlepass, which only slow by around 50%. Notice the difference in scale. We also notice that the bin code version is much more complicated to compile as it falls behind all the other implementations. This makes sense because it's doing full serialization and deserialization instead of just passing bytes around. Unfortunately, this compilation time increase doesn't manifest any performance improvement because most of the LLVM's optimizations do not apply to the simple code in this test module. Moving on to the macro benchmarks, we eliminated a few factors. First, we eliminated hot load and preload. They performed no difference in release mode, likely optimized away. We also removed dynamic Bytemuck as the static version performed strictly better and has the same capabilities. We also dropped the Singlepass compiler backend as it performed strictly worse and is not intended for deployment according to the developers of WASmer. It is instead meant for local development and rapid iteration. Since self-referential structs performed similarly to normal caching, we used them to implement all caching instances in the final program. This better represents a real object-oriented program where each policy is modeled as a single struct. In this graph, you can see the results of the Cranelift run of the macro benchmark. Each policy has results for each of the 6 techniques we tried, in addition to a result from the native run of it, using native machine code instead of WebAssembly. Similar to the micro benchmarks, caching performed better than the non-cache version for all runs. The gap between the native and WebAssembly implementations closed by many orders of magnitude, which implies that the performance degradation is primarily caused by the calls into WebAssembly, and not just the relative slowdown noticed by the University of Massachusetts paper. This slowdown appears to be relatively consistent, however, as the relative speed of each policy simulation was the same within a given ABI. For example, the least frequently used implementation was the slowest for each of the 6 ABIs we tested. The performance difference between each of the ABIs also shrank somewhat, most likely because the WebAssembly code is performing real work instead of a simple multiplication. Now, if we look at the LLVM version of the macro benchmark, we can see that performance didn't improve very much in comparison to the Cranelift version. Similar to with the micro benchmarks, the macro benchmark is likely just too simple for the LLVM to optimize effectively. And again, the relative performance of each ABI remained the same. Based on these results, we can see that for scripting applications or event-driven applications, WebAssembly is only slower within an order of magnitude, depending on which ABI you use. There are more potential options to explore for optimization for larger pieces of data, or to try different memory allocation techniques, or try the experimental WebAssembly reference types. However, when it comes to these simple data passing ABIs, the pair direct arguments is obviously preferred, and is actually used within each of the other ABIs we tested. Failing that, for more complex data, you would want to use a C struct, passing a static memory using tools like Bytemuck or the equivalent in your programming language. and this would only introduce a small slowdown in exchange for a much more flexible and expressive interface for your plugin. Failing that, however, bin code or something similar such as protobuf can be used, but because of their dynamic memory allocation, their performance is quite slow. If they could be adapted to work with static memory, you could actually get the best of both worlds in a sense by having an extremely expressive and powerful API while still being able to only make one call, like with Bytemuck. This has the added bonus of being much easier to generate code for other languages since there's already protobuf libraries for web development. There are lots of avenues for future investigations in this area of research. There's the potential to take a deeper dive into the implementation of WASMer or other WebAssembly runtimes to find potential optimizations under the hood. It would also be valuable to investigate the performance characteristics of these techniques using variable length data where possible. This fell outside the scope of this work because of the pair ABI's limitations. Further in the future, once they're implemented and stabilized, it would be useful to investigate the performance characteristics of the WebAssembly type interface and WebAssembly reference types proposals. The WebAssembly type interface would allow for foreign types to be passed into and out of WebAssembly in a more standardized way instead of using one of these ABIs. And the WebAssembly reference types proposal would allow to pass a non-forgeable reference into the machine instead of passing the object directly. These tests should also be performed against other WebAssembly runtimes, such as WASM time and the WebAssembly micro runtime, or WAMR. It would also be valuable to compare it against the runtimes found in browsers, although, to the best of my knowledge, those are not available standalone, so it would be a more involved task, due to the low-level access required in order to implement these ABIs. Finally, these techniques should be checked in other languages such as C, C++, C#, AssemblyScript, or any other language really that's compatible with WebAssembly. While there's a lot more areas that can be investigated and a lot more applications for this technology, I think that we've provided a good initial investigation into some basic techniques. Thank you for watching our presentation. The source code for all the benchmarks and graphs, as well as the complete set of graphs, are available at the GitHub linked on screen.